So I guess the system, so let's begin with a semi-simple Lie group of non-compact type. And we're going to get some discrete subgroup. And we're going to assume it is Zariski dense, because it's going to simplify many of the things I'm going to say, but it's not really necessary for most of the talk, I guess. So I guess the main dynamical system that we want to understand, of course, is the right action of A on this quotient. So it's a Cartan subspace. So I guess this is the main object we want to understand, and there's been a lot of talks on this system. Very nice talks by Sarkar and Chow-Sarkar and by Dang. So, but we're going to do an easier one, which is we're going to quotient by M. So here, what is M? Is the centralizer in K of e to the A. So when we picked a Cartan subspace, essentially we also picked a point, right? So if we think about this in the symmetric space, if X is the symmetric space of G, so I guess we'll begin by choosing a point, which is the class of K. And then we fix a total geodesic flat, a maximal. This is A, right? And M essentially is the rotations along this flat that fix the point O. Along that fix O. So this space is easier because what is this? So G mod M, essentially because of what I've been just saying. This is the space of parameterized flats on X. So what is a parameterized flat? It's an isometry. It's simply an isometry from A to X. So I guess we put a Euclidean norm on A for the whole thing to make sense. Depending on the invariant distance, we choose an X. And here the A action is just translations, right? I guess I put it like this, maybe. And so this space has what is called a Hopf parametrization, right? It has appeared many times in this conference already. So this has what is called a Hopf parametrization. So what is this? So essentially, if we have a parameterized flat, so what do we associate to him? So we look at one flag, which is essentially the equivalence class in the Fuster boundary of the image of the Weyl-chamber. I'm going to come back to that. Minus. Then the opposite Weyl-chamber, and then we got to pick some number. So this is what? So this leaves in the flags in general position, full flags of G in general position times A. So this is the class, right? So this here is the class of. So this. Yeah. So here, what I'm thinking of F, right? The equivalent is being bounded out of distance, right? And then we're going to put some vector here, which is essentially the Boltzmann cocycle that Jean-François introduced the day before, or yesterday, maybe? Yeah, yesterday. On this flag, and here I'm going to pick 2 points. So here it is our base point that we started at the beginning, and then I'm going to put the origin of F, right? So what is good about this parameterization, right, is that here the A action here is just translation on the last coordinate, right? So the main advantage A action translates as translation on the last coordinate. So maybe I put a quick maybe I give you just a quick example what's going on here in some specific situation, right? So when X, sorry. So when G is SLDR, say, or PSLDR, regardless, or PHLDR. So what is X? X, the symmetric space is going to be the space of inner products on RD up to homotopy. So what's a flat, a total geodesic flat? What is this? Essentially consists on, I have to fix the composition of RD into D lines. On D lines in direct sum. And what are you going to do? What is going to be the flat? The flat is going to be the set of inner. So let me write this as a sum of L on E of L, right? And so L are lines, and so the total geodesic flat is going to be the set of inner products such that these lines are orthogonal. Right? So if I want to parameterize the flat, I gotta fix an order to E, and fix some vectors in each of the lines. And so this order is going to give me the two flats, the two flags. Essentially, the flag is going to be the sum in one order, and the other flag is going to be the sum in the other order. Right? So now f of A plus going to be E1 containing E1 plus E2, contain, etc. And the other one is going to be on the other direction. It's going to be like this, right? And the last thing is the Bussmann cocycle. So what is the Bussmann cocycle? So we have a base inner product, and we have another inner product, P, which is the image of 0. And we have a flag. So what are we going to do? So we have our flag, which is a line containing a plane, containing a free space. So what are we going to do? We're going to look at, so this is going to be a vector, right? It has k coordinates. And so this has k coordinates. So the sum, so what I'm going to do, I'm going to look at the k space of the flag. In this k space, I have two inner products, O and P, and I'm going to compare their associated volume forms. And there's a ratio, and this ratio is the sum of the k coordinates of this guy. So this gives you a number, right? Which depends on k, and this is going to be, so this number, so this ratio, so this number, maybe, is the sum of the first k coordinates. So maybe just a remark which is going to be important later, that the sum of the first k coordinates only depends on the k space of the flag and not on the other elements of the flag. So here xk. Okay. So now we go back to our group. So our group on F has the smallest close invariant set, right, by Eve. So we're going to consider lambda its limit set, which is a closed, the smallest, sorry.
Can you say that again? I didn't quite follow your description of the cocycle. Could you explain it again? What do you do on the K subspace?
So you have, forget about the case, you have some vector space, V, and you have two inner products. They give you volume forms, and one of them is multiple of the other, right? And this is the number you put. You have a vector space with two inner products. Yeah, you restrict to this space. They have some volume form, and one of them is multiple of the other, and this is the sum of these numbers.
I see. Okay.
Yeah, that's exactly what it is. Yeah. Okay, so let's go back here. So we have the smallest closed invariant set. So this exists by Eve. Here, Zariski density is very important. And so, so here we have this space, right? We have this inside this G mod M, right? We have this new space, which has been called the non-wandering set. Which this is contained in G mod M. This is a natural subspace using the Hopf parameterization, right? So here, so this is naturally A invariant and gamma and lambda invariant, right? So when you go to the quotients, right, you have this them. Here, action. So in some sense, this seems like the set that contains all the relevant dynamics, right? So that's the moral. It's not entirely clear, but because the action outside the limit set need not be wandering, right? Probability is continuous in higher ranked. Ah, sorry. Yes, this is So this lives here, right? And when you quotient by lambda, this lives in here.
So you want to put lambda in the bottom line.
Ah, sorry. Yeah, sorry. Thanks. Anyway, so what do we do now? So what would I do now? I have my group, and I'm going to look at the limit cone. Okay, so now let me okay. So this is an open cone in the chamber, right? No empty interior. Might touch the boundary or not. So now let me assume that lambda is QI embedded. Assume. Quasi-symmetrically embedded. So I guess this might or might not be a natural assumption, but this is what we're going to work on right now. And so now what you're going to do, you're going to look at the limit cone, and you're going to look at the walls the limit cone intersects or does not intersect. So you're going to maybe you call it like that. This is the set of roots whose kernel does not intersect. So there's essentially two things going on. Either theta is empty, and then I don't know what to do. Then game is over, it's finished. We open another book. Or it's not empty. And so this is where we're going to focus on this. So if that happens, right? If that happens, we say that the group is theta Anosov, or maybe theta-Labourie Anosov, we should say, I guess. And so what happens? There are some very, very important consequences on this thing, right? Which is, for example, now this implies that the group lambda is necessarily worth hyperbolic. And so this is a result by Dey-Kapovich, 40. And the limit set, any of the limit sets would related to theta. So we're going to pick now any theta, which inside this is weird theta. So any of the limit set on this flag space is parameterized. Is parameterized by the boundary of the group. I guess I put here Hölder homeomorphism. Yes, so this is what? Yes. So now in this case, we're going to go to a smaller dynamical system, which is
What did you write before word hyperbolic?
Necessarily. Yeah, even I could have.
Not the first time I've heard that.
This is. Yes. Maybe that's better. Okay, so what happens now? So now we look at this subspace. So so this is very elementary. But when you have a matrix, right? When you have a matrix that has a gap between the first two eigenvalues, this implies that you have a very good control on the first eigenvalue, right? Having a gap gives you control on the first, right? And so this is saying that having a gap on theta, which is essentially saying that the elements of theta don't intersect the limit cone, is going to give you a very excellent control on what happens on certain combinations of eigenvalues. So this is where this space now appears, which is a vector space spanned by the fundamental weights. And so essentially, when we look at this, when we look at the linear forms here on this space that are positive on the limit cone, so this space essentially is essentially the length that we're going to control, that we're going to be able to completely control and understand, I guess. So this space is going to be the space of length, of possible length. And why do I call this a possible length? Because being in the interior, so being in the interior of this set, let me call this L theta gamma dual, I say. So being in interior, So being in interior of this set, is equivalent to, means essentially that you can compare the Jordan projections evaluated by phi with the translation length of lambda on itself. So here I put the translation length. On his Kelly graph. Okay, so now let me add a last piece, which is so the reason we call this A theta dual essentially is because the dual of some natural subspace of A, right? So we have our theta and we have A theta, which is going to be, we're going to define it as intersection of the kernels of these roots. So essentially, the choice of theta gives me a pair of opposite parabolic groups. These parabolic groups have a non-trivial intersection, which is called the Levy factor, and this subgroup has some center, and this is the center of this group.
You mean from theta complement? Advice from theta complement.
Yes. Thank you. Yes. Yes, so essentially what happens is that when you have your symmetric space, right, you pick one theta flag at infinity. You pick some opposite I theta flag at infinity. Here I is the position evolution. You look at the parallel set, which is essentially all flats that go from here to here. This is the parallel set of these 2 points. This parallel set is a homogeneous space, and this the group has some center, and this is the center of this. This A theta is the center of this parallel set. And what we're going to try to study is what one could call the theta parallel set dynamics, which is essentially moving along the center of this thing. Okay, so now our system that was like that, what was it? It was like this. We're gonna simply consider the theta limit set now, and I put a 2 also. Maybe I put theta below. To consider opposite flags, now theta and opposite theta flags, say. So I got a flag from theta and a flag from I theta, and they are opposite. And here I have this A theta, right? And here I have my lambda action. And A. Okay. And here I have A theta. So the main difference with this and and the thing above is that the action of lambda on this space apparently need not be proper, right? So here the action is proper, right? Because it lives here and it's a discrete group, right? And here the action a priori need not be proper. So in general, I don't know what happens. I think it might be something interesting to look at. So, but essentially what we're going to show, so what is the result, is that in the case we're dealing with, so namely lambda is theta Anosov, we can completely describe this dynamical system. So what is this thing? That's where I'm going. So the description will depend on a choice of length. Okay. So we go back to this length, these guys. So what are we going to do? We're going to look at, so we have our space, A theta dual, right? And here we're going to consider some sets. So essentially the first set we're going to consider is what I like to call the convergence domain. So we're going to look at all these forms, all forms, such that the Poincare series is convergent.
So it's like the analog of a domain of holomorphy, but it's a real analytic convex set. Domain of holomorphy for these analytic functions.
Yes.
I guess so, yeah. So what is this? Okay, so let me introduce another set, which is its boundary, right? And let me call it the critical, theta critical hypersurface, which is essentially is the boundary of this set, which I'm going to call Q, gamma, I guess theta, Q for critical, but also for Can. And so what's happening here? So we have a dual, and we have some subspace inside, which is this subspace. And on A, Jean-François defined this indicator function. And so he explained that it was concave and isohomogeneous. So you can look at the dual. So it's essentially the linear forms which are greater than this thing, and essentially gives you this set. So you're going to have a big set. Maybe like this. I don't know. We don't know exactly the shape. Just that it is convex. So this would be like the dual of psi. So essentially, forms which are greater than psi. And we're going to intersect that set with a theta star. And so what happens is that this is something that we can really control and understand.
In the definition, what is A of gamma?
Sorry. Yeah, Cartan projection for me is A. Yeah, I agree. Mu is a measure. I agree. Kappa is a constant. So I forgot the order. Anyway, yeah. This goes like this. Okay, so essentially, what's going on? Just go very quickly. I think I'm going way over time. So essentially what happens is that Q and the theta is a codimension 1 analytic submanifold. Closed.
You're not assuming it's a theta Anosov?
Yes. Yeah. So here I'm assuming lambda is QI embedded and the theta is a subset of this.
You're only assuming this. This does not imply theta Anosov.
It's equivalent.
Oh, this is equivalent. Okay.
Yeah. Maybe I should have said, sorry. So, yes. So if you're here and with this assumption.
Okay, I see. Because it means some circle part is a living okay.
Yes, exactly, yeah. So yeah, I should have said it, sorry. You need a theorem by Eve that describes a limit cone as a asymptotic cone. And once you have that, lambda. And it's a boundary of a strictly convex set. So here Zariski density is also very important. D is strictly convex. So essentially, there's many. So that, as Pratish was saying yesterday, so essentially the main input here is thermodynamics, and to apply thermodynamics, you need a very good dynamical system that is going to appear in a minute. But showing that this dynamical system is there is something we worked with Francois, Martin, and Dick. So essentially, to show this, I mean, yeah, there's input of many people, I guess. there's a way to see this also using some paper by some work by Ledrappier and Babillot. Okay, now so let me begin with the topological description of the set. Of the system, right? Sorry. So we have our length function, which we're going to pick here in Q. Yes, sorry, I forgot to say something else. I forgot to say something else, yes, sir. So when you have this linear form here, right, so you have your Q, which is over there. So this phi, we're going to look at the tension space at this thing. So I'm only looking. So maybe it's on a drawing in A theta, because it's going to be more clear what's going on. So look at the tangent space of this thing. So this is a hyperplane. So it gives you a line in the dual, right?
This picture is where is it?
A theta.
Of the dual, A theta?
Dual, sorry. Here, yes. So this tension space is a hyperplane in A theta dual, so it's a line in A theta, right? And so this line, we're going to call it U phi, say. So essentially what happens is that, okay, so this action is going to be properly discontinuous. So we're going to take the quotient and we're going to, so the action is going to be properly discontinuous. We're going to take the quotient, so this quotient is what? So what is this going to be? It's something that Patterson explained yesterday. It's going to be the unitary tension bundle of our group times the kernel of phi. So here, there's going to be a flow here, which is going to depend on phi, which is going to be a reparameterization of the geodesic flow. And there's also going to be some mistake, I guess, I would say, that lies here. So essentially, what one wants to understand, for example, maybe I should put it like this. This is a different kind of F, maybe write big F from, sorry. Holder continues. Let's just go on quickly. And so what's happening is that we're going to look at the action on this space. So this is going to be what's going to happen if you look at the action of curve phi on this space. Essentially, what's going to happen here, you're literally going to move along the fiber. So in some sense, the curve phi action on this guy is proper. It's really removing along the fiber over something. Right. And so the question is, what happens when you look at the action of this guy on this space? And so the dream would be that you're just moving along this flow, but that is not true. That there is a mistake that you make on the fibers, and this mistake is given by some Hölder function. Okay? So you have your flow here, and you have your fiber that's moving along, and moving on this guy is not going to be just moving along the base, but you're going to have some variation on the fiber. So this is what is called a skew product dynamics, right? So again, there's many people entering in this picture. So it's myself, but then there's also these guys giving the input of this flow being Anosov, metric Anosov, and then there's also Carvajales, and there's also a very nice proof, well, by Chow-Sarkar when theta is delta. They also give a proof of the result in their paper. Okay, so that's for the topological thing, and let me just quickly go to the measurable thing. Maybe I come here. Yeah, actually, I realize I'm not having that much time. Yes, that's what I'm thinking. Yeah.
So you will construct the map, or there is a map on your blackboard? You will construct it, or you have constructed it?
Yes. I mean, so.
There is a map here.
Yeah. I'm trying to think. So, no, I mean, at some moment you solve some cohomological equation to make everything so nice. So at some point,
your statement is that there is a map.
Yeah, sorry. Yeah, I'm sorry. Sorry. There's a map here, which is Holder. It's a bi-Holder homeomorphism.
I mean, if you don't use Hopf coordinates, it's this thing's an affine fiber bundle. And if you think about it that way, this is just a Holder continuous splitting. They're all cohomologous to one another, so he's picking one. And Hopf coordinates is like a good functorial way to pick one because it sees the Lie theory.
So it's you could say you construct it, but it's kind of, there is some cohomological equation that appears. At some point, some cocycle, some translation cocycle is homologous to integrate some function, for example.
But if we have not seen it, we can think this is trivial. It's not trivial. It means that this map exists. And
I'm not saying it's trivial.
Okay.
No.
Sorry? You said that your flow on U lambda is a row parameterization of the geodesic flow?
Yes. Yeah, so the point is, essentially, you describe the system as being, the point is being, it is a skew product over an Anosov system. And then you go and you study this guy, right? Which is much easier, I guess. So, but instead of talking, okay. Maybe I go very quickly because I promised Minshu that I would talk about their dichotomy, so I'm gonna speed up. So I'm not gonna say the second part that I was planning to say. Let me just go quickly to the following result.
But you plan to explain this map later, or just to know?
I could tomorrow. I wouldn't mind. I wouldn't mind. You know. I wouldn't mind. So tomorrow actually, so there's this conversion, this critical hypersurface, right? So essentially, of course, I mean, we've seen that a lot of information is contained in this critical hypersurface, right? It's a lot of information. And so trying to give a geometric meaning to a point in that critical hypersurface is kind of a long-term program, right? So you pick your phi, right? You pick your phi, which belongs here, which is a length function. Oh, sorry. And so it has a critical exponent. So this guy belongs to Q, right? So having a geometric meaning for this number is kind of a program that I'm interested in, and I was thinking about talking more on that side tomorrow, but we will see. So anyway, so so dichotomy. Okay, so something that happens in Anosov groups is that every point on the limit set is conical. I guess I can. So, okay. So let us talk about directional conicality. This is a very beautiful concept from Burger-Landesberg-Lee-Oh. So I really like this concept, especially when we were thinking about something with Bay at the time, and we realized that this was kind of the input we were missing. So what is this? So I'm gonna just pick. Let us say that we have the maximal case, so the minimal parabolic case. Just to simplify things for the moment, and then I try to do something else. So we have our limit set, right? And we're going to pick a point here in our limit set, right? And so what they do is define some notion of conicality for this guy that is going to depend on a direction of the limit cone. So x is going to be u phi conical, meaning yes, u phi is the direction there so here now a theta is just a, right? If what? So maybe I can have it like this. If I have a sequence, a conical sequence, if exists, conical sequence. So this I'm thinking about lambda as an abstract group. So here conical is just usual conicality for hyperbolic groups. So what is the new condition is that you're going to look at the Jordan projections, and you're going to ask them, you're going to require that they lie in a small tube around this direction. So we have phi, we have this, we have the limit cone. This is u phi. And we're going to have a small tube. Yeah, maybe I'll use other colors. So x is going to be conical if there is a sequence going to x in the group, such that the Jordan projections lie on this thing, on this tube. I'm not asking the sequence to be. Sorry, Carter. Yeah, sorry. Thanks. Yeah, thanks.
Not a cone.
Exactly. That's the main point. That's the point. It's got to be really, really nearby. So Kant indicator function is counting on a cone, right? And here you're counting on a tube. So what is the result? So maybe I just recall that to each phi there exists a Patterson-Sullivan measure, which is supported on the limit set. So maybe since we're looking at theta to be the whole set of roots, we can just look at Kant measures. So what is the result? It's very cool. So they do more. They don't only treat the delta Anosov case. They do Zariski dense subgroups, and they have some statement there, which is kind of what I'm going to say. But in this situation, is much cleaner. So the following so they are equivalent. So we have the following facts. So the following are equivalent, which is the rank of G is smaller than 3. This is equivalent to our flow over there flowing by U phi being ergodic with respect to the natural measure that appears, the BMS measure with respect to this guy. Is ergodic. And this is equivalent to what? Conical points have full mass. And a series along the tube so this should be infinite for some r. So the statement is not over. It doesn't end there. Yes. Ah. No, R. It's the size of the tube.
Okay.
The size of the epsilon neighborhood. It's the T neighborhood. Yes. So essentially, every point is U phi conical, if and only if this flow is ergodic, and if and only if G has rank at most 3, and if and only if this series converges. And actually, it's much more because the negation of this is pretty strong.
So sorry, there is no critical exponent here because
phi is in Q. Yeah, phi is in Q. Thanks. So essentially, its critical exponent is 1 by definition. Yeah. So the negation of this is much stronger than what it looks. So when you have this, so the equivalence is that it's stronger than not being ergodic. It's totally dissipative. So every point lies in a positive measure set that is wandering. And this guy has 0 measure. and the sum is convergent for R.
This is under the assumption that V equals delta.
Yes. Yes, sorry. Yeah. So this here, maybe I put it here. Yes.
I'm sorry, is there a... The 2 gamma is the risky density?
Yes, yes. Since the very beginning. Lambda is a risky dense, so in this case it's going to be theta Anosov. So maybe just give a hint, given that I spent all this time talking about this, give a hint of why this is true. So essentially, so the 3 there, so the rank of G is going to be rank G minus 1 over there, right? And so you have a skew product over Anosov flow with some fiber, right? And now you got to think about what happens when you take a random walk in Rn. In Rn, the random walk is recurrent in R2 or totally dissipative in R3. So the 3 there is a 2 there. And that's kind of the reason, I guess that's kind of the reason why this kind of result holds. And then, and maybe... Yes, sorry, yeah, this is, yes, analogous of Hopf-Sushi-Sullivan dichotomy. Yeah. And I think everybody must be pretty hungry, so I guess this is a good time to stop.
Any questions?
So when you talked about this convergence domain and some problems about that, and this generality level that tells you a lot of you something about that is strictly concave and analytic. Yes. Can you say something more quantitative, like about the Hessian of the function, if it's negative definite on like the tonal directions or something like this?
Yes, I
mean, can you say something quantitative, like the Hessian being negative definite? For instance, you know it's strictly concave, but it doesn't need to be negative definite.
No, but I mean, the way you prove it is that the Hessian is negative. The way you prove state convexity is essentially that, right? Essentially, you have a pressure function, right?
Right.
And the Q is the level set of a pressure of pressure equals 0, right? And essentially, you show that the second derivative of pressure is positive on the tangent space to this guy.
But and the same as saying for the growth indicator function there?
I think, yeah.
I don't think that part is there.
No, but I think, yeah, it's a pity François-Ledrappier is not here. So essentially, yeah, it's a rational transform, something like that. I mean, there is some... I'm pretty sure there is some relation. But I should think about 3. I will push that François-Ledrappier. He'll be here tomorrow.
Any other questions about this? So in this picture, you're saying that if the flow on the full here is that flow, that the flow on the right is ergodic, right? On U lambda?
So this flow, yeah, this flow is a mixing. Yeah.
This flow is ergodic, and then there's flow on the bigger space.
Yes. Exactly. Yeah. Exactly. Yeah. So exactly. So this flow is. Yeah. This is what I was saying earlier. Like, so the dream would be that this flow was exactly this part. I mean, like, right? That you have the kernel here acting trivially here, and then the recurrence part just being this part. But it's not true. When you move along the base, the fiber is going to move a bit, and this flow is going to be more complicated.
And we're meant to think of this capital F as like a random walk in the fiber or something?
Centered on the walk. So yeah, but I was going to add a measurable description, but F has mean 0 essentially for the natural measure here. So F is kind of, it doesn't go away. F It moves a bit in the fiber, but sticks around 0.
So the question is, the dichotomy is like a dimension less than 2 or larger than 3 for the kernel of psi.
Yeah, yeah. This, I mean, you can make this more correct.
More precise.
I could also mention we use actually local mixing result because local mixing tells you the rate of actually recurrence. And this is where you see the dimension.
Thank Andrés again.